Hi everyone, I'm CJ,
And I'm Peter.
and today we're going to be talking about why magnetic fields might actually be a major requirement for life to exist on a planet, and how we're starting to search for magnetic fields beyond Earth. We'll start by looking at how Earth's magnetic fields works, and then we'll talk about why magnetic fields are important for life, and finally, how scientists are trying to detect them around other, planets.
First, let's look at how Earth's magnetic field is created. It comes from what's called a geodynamo, which means that inside Earth, the outer core is mostly made of liquid iron and nickel. Because the core is moving and the metals conduct electricity, it creates electric currents. And as we have learned in class throughout the year, electric currents create magnetic fields. In Earth's case, the combination of Earth's own rotation and the molten metal's convection in the outer core sets up a strong, large-scale magnetic field. Earth's field at the surface averages about 25 to 65 microteslas, which we're about to explore a little further.
We can make this comparison between this diagram with the dynamics between this current going through a solenoid and its resulting in magnetic field. While it's not an accurate way to calculate field, simply because we can't calculate the number of turns in the Earth's core, the overall conceptual relationship between current and field remains the same.
Instead of using a solenoid, we decided to try a magnetic dipole or giant bar magnet kind of method. We found the formula of magnetic field for this as 2m times mu naught over 4 pi r cubed. R cubed was the radius of the Earth cubed, and m is the magnetic dipole moment of the Earth. When we plugged all the numbers in, we got an answer that was about 60 microteslas, which falls in between the range we stated earlier.
Earth's magnetic field extends outward and informs the magnetosphere, a giant bubble that protects the planet from the solar wind, streams of charged particles constantly coming from the sun. The magnetosphere deflects most of the solar radiation. If it didn't, particles will collide directly with our atmosphere, stripping it away over time in a process called sputtering. This is one reason why Mars, which lost its global magnetic field billions of years ago, now has a very thin atmosphere, less than 1% of Earth's atmospheric pressure at the surface. Without the magnetic field, Earth will likely have lost its thick atmosphere, and the surface would be bombarded by radiation, making life as we know it extremely difficult.
This brings up an important point. It's not just enough for a planet to be at the right distance from a star, normally called the habitable zone or the Goldilocks zone. If the planet doesn't have as much of a magnetic field to hold on to its atmosphere and block radiation, it may still be uninhabitable. The magnetic field also helps maintain stable temperatures, allow water to stay liquid at surface, and shield life from dangerous radiation. Without this protection, even if a planet has oceans, chemicals, and all the other ingredients for life, then the high energy radiation would sterilize the surface. And this is also maybe a reason why Venus and Mars, which are still inside the habitable zone of our solar system, may be hostile to life.
So, if magnetic fields are really that important, how can we find them on planets orbiting other stars? It's really difficult because magnetic fields themselves are invisible, but there's a clever workaround: auroras. When solar wind hits a magnetic field, it can create an auroral radio emissions, basically radio waves generated by the charged particles spiraling around magnetic field lines. Scientists have already detected radio waves that have seemed to come from planets 40 to 100 light years away. These are just tentative detections, but it's exciting because it's the first step toward being able to see magnetic fields directly. Future observatories like the Square Kilometer Array should be able to detect even weaker magnetic radio emissions, making it possible to map out which exoplanets have strong magnetic fields.
Magnetic fields exist everywhere in the galaxy, in stars, nebula, and even between the galaxies. But when it comes to life, the key to having a planet, or having a habitable planet, is having a strong, stable, and very long-lasting magnetic field. This usually requires that a planet has a rotating, metallic, and liquid core, with enough internal heat to keep the core moving for billions and billions and billions of years. This requirement might actually limit how many planets are truly habitable, even beyond the ones that we find in habitable zones.
So, to summarize, Earth's magnetic field is a crucial shield that protects the atmosphere and life. Planets without magnetic fields may lose their atmospheres and become sterile, even if they're in the habitable zone. Scientists are now developing ways to detect magnetic fields around exoplanets using radio astronomy. In the future, looking for magnetic fields could be one of the main ways we search for signs of life. And as tools improve, magnetism might turn out to be just as important to life as liquid water. And thanks for listening.